Okay, very good. So we can continue with the Amplitude lectures now, and I would like to start from the point at which we stopped yesterday, namely by providing a simple example of a calculation at one loop in which you use unitarity methods in the sense I specified yesterday. So in particular, I would like to look at amplitudes at one loop, 4 points, for n equal to 4 super mils, and external gluons. This is a simple workable example, and in particular, we will focus on a given ordering of the external states given by a trace. So essentially, we're going to be looking at a one loop example in which there's disordering given by the external states. And as I explained yesterday, the general idea is to look at the integrand and make an ansatz in which we have the denominator, the structure originating from the propagators, and here, which in this particular example would be the following. And here we put in the numerator, presumably with some free parameters, a function of, this would be polarization, or if you prefer, spin-velocity variables, external momenta, and although in this case will not be necessary, also loop momenta can also appear into this. So the idea is to use constraints from unitarity to fix this particular n, which is going to be a polynomial of the kinematical data. Very good. So the reason I have picked this example is that, of course, this is particularly simple and yet gives us an idea of what these techniques can be used for. So namely, we're going to evaluate the S cut here. And we're going to consider situations in which leg 1 and 2 are on one side of the unitarity cut. These are our cut propagators. And then we have 3 and 4, and we need to preserve the ordering in here. We're going to consider the simplest cut and then comment on the other cut that this amplitude has, in which the helicity of the external particles is assigned so that you have 1 and 2 with the same helicity on the same side of this cut. And also, just to give labels, I'm going to label this as L1 and L2. And the expression for this originating from the unitarity relation is, aside from integrations, of course, in the variables. Here, since we're looking at the integrand, we write the integral just to remind ourselves that we are dealing with a loop level amplitudes. Here we're going to have the product of 2 3-level amplitudes in which the states are assigned, as one can see from the figure of the cut. So namely, we're going to have here, so there's going to be a minus L2, 1, 2, and L1. Momenta for me are outgoing. And I get a couple of questions about this, so just to remind you one more time, in this course I'm taking all momenta as outgoing, and this can confuse you in the sense when you are thinking about this as a 2-to-2 scattering. So you want to take something as incoming, just flip the helicity for the corresponding, and then you get the process which you would obtain through crossing. Okay, having specified this, we then have L2 without a minus sign, and then L1 minus L1, 3, 4, and this would be the amplitude at 3 level that enter. And let me like label this with the elicities so that we can use the MHV formula. And of course, this is done as we mark this as S-cut. So here, even though I'm not explicitly using the Katowski condition, this is to be understood as I can use the on-shell condition for simplifying or writing down these amplitudes. And then these cut propagators will be replaced by the corresponding delta functions. So the first question here is what exactly can go through the cut? In this particular configuration, we can see that while we have a minus and a minus, actually this particular cut is the same as Purian-Mills theorem. We will need to have plus polarizations in here. And here there's 2 pluses, I need 2 minuses in here. So effectively, we just have one pair of particles which can go through these states, which would be positively polarized gluons here and negatively polarized gluons here going through this. Very good, and let me just say for completeness here that the integration is going to be over, say, L2, and then L1 in this particular case is L minus K1 minus K2. So that's the relation between the labels there and the integration momentum. Okay, so just to continue for a setup, then right away we're going to rewrite the integrand here as the following combination of amplitudes which are built out of just applications of the MHV formula. Here we just need to have the corresponding cyclic ordering, and there's an L2, 1 over L1 squared, and here we have L1, L2, or L2, L1. And here we get L2, L1. This is a 2, L2, L1. L1, 3, 3, 4, and the last one here on the corner is 4L2. Okay, very good. So questions about this setup before we do the calculation. These are, I don't want to say elementary manipulations, but there's a little bit of algebra here. But before, I would like you to inspect the setup and see if you're happy about this. Everybody's happy, or do you have questions? Good, very good. So then we start, we note a couple of things. So we note, for example, that we look, okay, as a general strategy before we start writing things and using them to simplify, my general strategy here would be, I want to bring this integrand as close in a form as possible to my target here, right? So I'm trying to, well, I already have an L2 with my convention here. This is the L2. It's the same as L, and then L minus K1 minus K2. So these I already have, so I need to pull out these 2 elements from some clever manipulation. So the clever manipulation is that we have here 2L1. And this is, I mean, almost immediately related to something which has the square brackets on the numerator, and then this will be 2 K2 that into L1 using my notations. And then keep in mind we can use the S-cut condition, okay? So we write this as, say, numerator, we rewrite the denominator as L1 plus k2 squared. This becoming, and here I want to just note that this is true only on the S-cut. S-cut meaning that these two elements are taken to be on shell. Okay. Very good. So this is the same can be done in 4L2. So again, we write this as L2 and then this would be L2, the scalar product of L2 and K4. We write this as L2 plus K4. And again, we note that here the S-cut conditions have been used. Okay. Very good. So we continue just by noting a couple of other elements. We also have here that L21. So in a sense, we are using this for simplifying the elements, the brackets which we find in the denominator, right? And try to relate them to the target expression coming from our ansatz. So in this particular case, L21, we write this as L21. So note the ordering in here, and this becomes L2 minus K1. Again, as on the S-cut. And we see here that I want to have a minus sign, and for this reason, I keep the ordering in here, right? Okay, so the last element which needs to be rewritten is L13. Since we're having all options, and this will become again L13 square brackets divided by L1 minus K3. Again, this is squared, and this is on the S-cut. Okay, so the use of these relations, this use of this relation allows me to rewrite the cut, the S-cut, in the following form. So we are going to have, here we write L1 squared, here we have L1 plus K2 squared. Here we have L1 minus K3 squared, and here you have L2 squared. Okay, which by use of momentum conservation is the same structure which you see there in the denominator. And then we write the rest as L2, L1. So we have still those which are left in here. And let me just note that, I mean, obviously these two up to a minus 1. This I can simplify further. I have here L2 plus K4 squared and L1 minus K3. Sorry, L1 minus K3, I already used it, so L2 minus K1 squared. So I've used all the numerators which I've obtained over there. And I would like to do one additional element in here. So a very good strategy here would be to, since we know that the helicity weight of this amplitude at one loop needs to be the same as 3 level, just let's pull out a factor which is equal to the amplitude at 3 level. So here, I just want to pull out a factor which is 1, 2 to the 4th. And then I want to write the 1, 2 is here. It's fine. It's already there. And then there is a 3, 4 in what I wrote here already. And then, of course, I multiply and divide by the two elements which were missing, namely the 2, 3, and 4, 1. And then I have to make sure here to multiply by 2, 3, and 4, 1. So writing in this way, this becomes L2 and L1. Then we have L1, 2, which is taken from here, of course. And then 2, well, I use the 2, 3. I'm trying to build a trace, so I want to keep pairs of the same spinors, angle, and square consecutive to each other. So I put here the 2, 3, and then I look for something which is from the with the 3, and I'm going to do here L1, 3. There's going to be a minus sign, which I need to consider. And then there's going to be here an L1, L2. L2, 4, which is here from there. Then I'm going to do a 4, 1, so that I don't forget it. And then the last one is going to be an L2, 1, which is L2, 1. So I've just let me make sure I have not forgotten anything. L2, L1, L1, L2, but there was a minus sign in here, so that is fine. 2, 3, 4, 1, and then I have this from here, L2, 4, L1, L2, 1, L1, 3. So nothing here has been forgotten. And of course, I always have to remind myself that this is the kinematics for the S-cut is to be understood in this expression. So this evaluation now allows me to express the S-cut as minus I. If you put a factor of I in the MHV amplitude, then you have to remember about this. So this would be the 3 amplitude. And then this would be proportional to what is essentially a trace. If you want to think about this as a trace of gamma matrices, you just have to remember that a chirality projector is inserted in here, because we are dealing here effectively with two-dimensional spinors. And then here, all these objects are contracted with the gamma matrix. So I should put a bar on it, a slash on it, but for easy, for readability, I will hope that we'll understand it this way. So it's L2, L1, K2, K3, K2, K3. Here there's a minus sign because I flip L1, L2. L2, 4, it's already coming from that. There's a K4 in here, and then there is a K1. And then to finish the trace, I need this flip of sign. I mean, flip the ordering, which means that there is no overall sign which is being gained. Okay, very good. So I managed to write everything as a big trace, and now I just diligently write here the denominator, sorry. And okay, very good. L1, and keep in mind that these, I kept them, but by momentum conservation are actually equivalent to the other two I wrote there. So this is the same as this, and by momentum conservation, this is also the same as this, and again, the cut condition has been used. Okay, very good. A little bit of extra work remains to be made here, but so far, is everybody happy with these manipulations? It's organization, but I don't think there's a lot of depth in what I've done other than manipulating objects which perhaps were not familiar until a couple of days ago. So let me know if some of this looks strange. Personally, I find it extremely difficult to keep track of signs in here. I always have to double check multiple times. Okay, so next. One thing I would like to note at this point is that we have a lot of loop momenta in the numerator in this trace, but we can actually, given the fact that these L's are consecutive to each other, it's easy to note the following thing, that, of course, on the cut, using the cut conditions, L1 and L2 are not independent. So L1 and L2, yes, sorry. Okay, so what I mean is that there's a projector here. So let me be a little bit more explicit about this. So a minus projector. What is a minus projector? So this is 1 minus gamma 5 divided by 2. And then these are all contracted by gamma matrices. So maybe let me do it like this so that everybody, I think, understands. Okay. But why? Why is it there? Why is it there? Because this is the same as having a sequence of not gamma matrices here, but sigma or sigma bar, because this is where these are two-dimensional spinors, right? So in other words, okay, one can say with different wording that we are using via spinors and we are using a chirality projector to project to a certain chirality in a position. Why did I put a minus before the L2 in that particular case? Because the L2 projector here starts with the angle. Hang on, L2, L1. So yeah, so this is starting from. Hang on, should it be a plus projector? That is an interesting question. Okay, so it should be the sigma. The sigma has starts from an L2. Yeah, it should be a plus projector. Very good. Why do I say that? Because the L2 here is where can I put it? Because the L2 over there, we note, okay, that 1 plus gamma 5 divided by 2. So this is the plus projectors of L2 is equal to, well, we are starting here with the L2, the plus polarization, the plus spinor, and we have the L2 here, okay? Which is exactly, once you flip this bracket, the structure you find in this trace. The reason why I don't care so much about plus or minus projector is that the job of this thing is simply to make overall numerical factor going down from 4 to 2, because we are tracing not over the space of four-dimensional space, but to a two-dimensional one, effectively. Okay. So what I was about to say before is that we use the expression of L1, of L2, let's say, in terms of L1, which is still written there. This, together with the fact that L1 is null in on the cut condition, and on the cut, again, we can write this as L1 K3 plus K4. Very good. And a similar manipulation, which now will be used for this part, L1, L2, is going to be, we can write this as expressing K2 in terms of, sorry, L2 in terms of L1, and this is something that, in a sense, involves a choice. I mean, you can do this in different ways. You can write it in this way. Okay. Please stop me if you have other questions. Otherwise, I am ready to rewrite my trace in the following way. So can be rewritten as trace. Now I have a plus of K2 L1. So there is, so I start from L2 and L1. So I write this as K2 L1 because I remember that the last one was in the trace was a K1. So it's a cyclically adjacent to the another K1. So only this term survives. This is equal to 0. And then there is a K2, K3. Further, L1, L2, I use the other relation. So this becomes L1, there's a minus sign, which is this minus sign, K3. Then there is K4 and K1, which is quite important for having K3, K4, K1. Okay, very good. So this is a very simple or a simpler version of the same trace for the following reasons, that we can see that it's enough to anti-commute K2 once through L1, and then you get a 0 result. So you can do this just by using anti-commutation relations. There's a 2 coming from the Clifford algebra relations. Minus is inherited from before, and here you get L1 dot into K2. So I've anti-commuted this, multiplying a shorter trace, K2, K3, L1, K3, K4, K1. Very good, 2, 3, L1, K3, K4, K1. And again, I remind you that there are gamma matrices in there. And then the next operation is we're doing this another time, and now we want L1 to anti-commute with this K3, so that the final result will also be proportional to that. So now we have L1 dotted into K2, L1 dotted into K3, and then we have a trace with 4 elements, which we can very easily express. So this is, again, a plus trace. And we express separately, so the trace itself, perhaps the most pressing calculation. This becomes where we take the sum of the scalar product of the 2 lines which are next to each other, so 2, 3, and 1, 4. So this is t squared with a factor of 1/2 plus s squared, 1, 2, 3, 4, minus the case in which they are not adjacent to each other, and this would be u squared, which is in turn rewritten as minus st by using the fact that the sum for massless states, mass of the sum of s, t, and u is equal to 0. Here, these 2 objects are readily, shall we say, rewritten, including a factor of 4. We should make this parenthesis a little bit larger, as L1 plus K2 squared L1 minus K3 squared. which are indeed needed to sort of simplify the excess of inverse propagators in the denominators, which you have over there. Yeah. So what the gamma 5s in the trace does is, so okay. Sorry, so what the gamma plus in the, or the gamma 5 in the trace does in this particular case is to reduce. So we have a factor of, let's say, probably it's just better if I write the identity in a more extensive way. So we are familiar with the identities that you have which is equal to 4, coming from the dimensionality of what we have there. And then we have eta mu nu, eta rho sigma, plus eta mu sigma, eta nu rho, minus eta, and now the indices is mu rho, eta nu sigma. So now that we are adding a certain chirality projector, what this essentially does is reduce this to 2, which is, yes, the identity we have tried. Why does this reduce this? Yes. Yes, indeed. Indeed, yes. Yeah. Yes. Indeed, indeed, indeed. Okay, very good. So that's another, yeah, that's another way of saying that. Yes. Indeed. So this becomes the 1/2 coming from the projector, which is a factor of 1/2 in there. Okay, very good. So is everybody on the same page in here? Then I can, let me just write the result in one line, and then we discuss what the implication of this is. So we have the S cut, which is equal to A, the 3 amplitude, ST, and here we have what in the other day I indicated as ICE4 of ST evaluated on the S cut. Okay, where now the I4 has been, I mean, the important, shall we say, part has been that, as we can see, there is no longer any loop momentum after this manipulation has been made in the numerator. And we are having just the propagator structure, which corresponds to the scalar integral. We have no tensor structure in the numerator, which is the I4. And of course, this holds on the S cut. Okay. So in order to continue and simplify this further, we have to evaluate also the other cut, which this structure has, namely the T cut. I mean the cut, which goes over here. Actually, so far we point out that this cut condition is satisfied by choosing, since I still have the calligraphic n equal to I st A3. Now, what should be verified is that, and I'm not going to do it here now, but this is a straightforward exercise, although let me point out one aspect about this exercise, that this particular choice for the numerator also satisfies the T-cut condition. So we have a simple ansatz for our numerator that satisfies the cuts in all channels. And this allows us to essentially write this write the one loop amplitudes in terms of with the same relation, having just removed the cut condition over that. Now, there is a little bit which still remains to verify about this, and which I will let you do as an exercise, if you like. Namely, the fact that indeed also the t-cut corresponds to gives you the same result, essentially, replacing S with a T in here. And somebody can object to that because it requires slightly less trivial manipulations at the level of the numerators. For the following reason. Here I've used a very simple property of this amplitude, the fact that having the same polarization on the same side of the cut, so to speak, forces me not to exchange too many things. So one thing you can object about this calculation, or this part of the calculation, right, there is the fact that, well, where does n equal to 4 come in exactly? Because I have done just a gluon amplitude. So actually, I would encourage you to do this as an exercise. And you'll have to consider all the exchange of states. Because if you are considering the t-cut, namely, would be something horizontal like this, you would have 1 and 4 on the same size, so everything can be exchanged to the cut channel. And you would have different contributions. The only non-trivial part, aside from what you've already seen, which is slightly non-trivial, would be the fact that you would end up with the following structure in the numerator. So you would end up having that once you add up together all the structures, all the helicity brackets which can be exchanged, you end up having something, you have many terms, and then you realize that this is the fourth power of this particular combination. You would have 1 and 2 in here, and then you would have 1L2 and 1, 2. This would be the fourth power. Now, by a Schouten identity, this is precisely the same as what we see here in the numerator. Namely, by a Schouten identity, this would be a 1, 2. And then there it would be, it would be more the same of this numerator. So taking that into account, the calculation goes through along the same lines, and indeed one can verify that this ansatz for a one loop amplitude satisfies all the cut conditions. Yes. Mm-hmm. Mm-hmm. So no, A3 in here is with legs 1, 2, 3, and 4. So A3 is precisely, where did I put it? Yeah, so A3 does not have any dependence on the loop momentum. The only dependence on the loop momentum is in this integral. Yes. In fact, this is something almost, I mean, I just multiply by A3, or rather put an A3 in here to have the proper weighting of the little group scaling. Okay. Yes, that is completely pulled out, and it's a good way of writing the loop level amplitudes, because you know that there's going to be certain transformation property under helicity, and that's the same as tree level, so you just express the loop level amplitude as 3 level times something, and then the interesting part is this, the integral. Okay, other questions about this? Was there anything else which requires justification? Oops. Okay. So there are a couple of additional things I would like to comment on. So one thing is that there are different ways of fixing this contribution. In this particular case, I've used, in a sense, an old-fashioned cut, because this is a cut involving two internal lines. If you can do the same calculation, however, in considering an additional number of cut conditions. In particular, you could consider a quadruple cut, or a cut in which all the internal lines are cut. And that would be something which, on the one hand, still allows you to get to the same result. On the other hand, requires an interpretation different from the one from unitarity. This is something that you can write as TT dagger, right? Either this is T and this is T dagger, or the other way around. Whereas if you start cutting more than two propagators, this particular case, you would have to use what is known as a generalized cut. Or if you like, this is part of the generalization of the unitarity method, which makes the use of the word unitarity slightly misleading. This is more integrand reconstruction. And the integrand can be reconstructed by putting whichever sub-amplitude on shell within the loop integral. Another questions which deserve some commenting on is the nature of rational terms. So a very common objection, or something that can be remarked at this stage, is the fact that it can be asked, at least, are all the contributions to amplitudes cut constructible? In particular, if we are having rational terms, at least in 4 dimensions, are terms that you don't expect to have any cut. So what can you do in this particular case? There are generalizations of unitarity methods which require us to depart from 4 dimensions. In order to do this, let me mention a simple example of rational term. So in principle, one can split the loop momenta in the following form. Since loop in momentum integration is in d-dimension, this is part of dimensional regularization. We can express the loop momenta as a minus 2 epsilon dimensional part and a 4 dimensional part. Don't get too weirded out by minus 2 epsilon dimensional part. Just consider doing everything in d dimensions, and then by analytic continuation going to whichever value of d you want. This implies that your loop momentum really will not be massless in 4 dimensions, but will be massless in 4 minus 2 epsilon dimensions. So in other words, the 4-dimensional part of your loop momentum will obey an equation involving a mass term, which is called mu in this particular notation. This is what is known as a mu term. An example of an integral that is leading you to a rational term is an integral of the following form, when you start having a mu term in this particular case. Actually, so it would be a 4th power. So in some situations, you can end up having rational terms which are originated by this fact that loop momentum needs to exist away from 4 dimensions. And we cannot enforce L4 equal to 0, squared equal to 0, strictly speaking. This has a consequence on the fact that when you're having a 1-loop amplitude, for a rational term, by dimensional reasons, even if you have a rational term in 4 dimensions, you are writing this in the following way, say in this particular case in which you have S and T as independent variables. So if we are having something which is massless, by dimensional reasons, the amplitude, I mean, since it is coming from an integral of a certain number of vertices and propagators, and then there's this integration in the dimensions, the general amplitude in one loop for a rational term will have something of this form by just dimensional analysis. What does this mean? It means that there is a branch cut, but the branch cut doesn't show up at order epsilon to the 0, it shows up at order epsilon. So in other words, to detect, at least strictly speaking for a massless theory, if you want to detect rational terms, you need to keep track of terms of order epsilon in your, for example, 3-level amplitude. And you do that keeping into account that the amplitude which you are getting from 3-level, it is the external lines which correspond to a loop momenta. They are not, strictly speaking, existing in 4 dimensions, but they have this. They are not massless in 4 dimensions, but they obey this relation instead. So those rational terms can be detected, but they require you to keep track of extra powers of epsilon, where epsilon is the dimensional regularization parameter. So I have an explicit example about this in the notes, which unfortunately I will not be able to cover, but I would encourage all of you to look through that. Actually, the example is an helicity amplitude in which all helicities are the same, say a minus. And in the loop, we have a complex scalar circulating around. The 3-level amplitude, you can see it right away. In this particular case, in 4 dimensions, strictly speaking, are equal to 0. However, they are equal to 0 only to order epsilon to the 0. When you start taking into account the fact that the momenta circulating in the loop is d-dimensional, then you start having contributions to the 3 amplitudes here, which is proportional to mu squared for both amplitudes. If you do all the math, you figure out that rational terms can be detected in this way. And a very common misunderstanding of unitarity methods is that cut constructability doesn't let you detect all the terms. For a massless theory, you can do that, but you need to be operating in the dimension that is using the dimensional unitarity. Okay, very good. I think this is a good moment to stop. Let me know if you have any questions. I will stick around, and we will recombine in 10 minutes. Okay. So we have approximately three hours left in these lectures, and what I would like to do now is to start the last topic, namely an elementary introduction to some tools for calculating scattering amplitudes in gravitational theories. And this is going to be the last of big topics, or if you wish, chapters, which I'll be able to cover in these lectures. Okay, so let me start with a bit of a motivation here. So the perturbative structure of gravity seems to be much more complicated than the one-off gauge theory. Just if you need to have some motivation in this front, well, if you look at the Feynman rules for Yang-Mills theory, we have, aside from the propagators, we have 3 vertex, we have a 4 vertex, and that's it. You look at gravity, and you start having that there is a cubic vertex. Let me indicate the gravity in a slightly different way here. And then there is a quartic vertex, and then it doesn't stop there. This is not polynomial action. So you start having more and more vertices. It doesn't stop. And then you look at the vertex, and you have the Yang-Mills vertex can be written, is standardly written with 3 terms in the cubic one. Here depends a little bit on how you write this, but this is of the order of magnitude of 100 terms. So just by looking at the Feynman diagrammatic here, or the Lagrangians if you prefer, you see that there is a huge increase in complexity in dealing with gravitational theories. However, it turns out, and we have already, I think one of you has asked me a question in one of the previous lectures. Let's try to write down the amplitude for gravity at 3 points, and we have seen that number 1 is very simple, and number 2 is also the square of the amplitude for Yang-Mills theory. So there is something there that seems to be not so visible at the level of either action or Feynman diagrammatics that leads to dramatic simplifications. And this is interesting. So taking one step backward here, I have to tell you a little bit on how to get a perturbative formulation of gravity. Our starting point would be the Einstein-Hilbert Lagrangian here, normalized, if you want to get this, with 2 over kappa squared. That's the standard that's normalization usually used in amplitudes, where you have that kappa squared is equal to 32 pi g Newton. And then when you have a perturbative situation, what you're doing is considering perturbation around the flat or Minkowski spacetime, where we are having that your metric becomes Minkowski metric plus a perturbation which is proportional to kappa. So this is your graviton. And a very interesting property, if we want to treat this along the same lines of amplitudes in gauge theory, is the fact that there is a principle equivalent to gauge invariance, namely invariance under linearized diffeomorphisms. So we know that general relativity is based on invariance under coordinate transformations. These coordinate transformations take the form of a coordinate going to another coordinate, x prime. For simplicity, we now consider infinitesimal or small coordinate transformations in which you're having that x prime is equal to kappa, and then xi. And then we have that, of course, g mu nu is supposed to transform under this coordinate transformation as a metric is supposed to transform. In terms of the relation between, I mean, the way a metric is supposed to transform under coordinate transformation. And then if you plug this in the infinitesimal coordinate transformation, which you had before, you are getting that this implies, just by expanding in kappa, this implies that your h mu nu transforms in this form, which very closely parallels or resembles a gauge transformation for gauge theory. Namely, this is the gauge invariance, which corresponds not to a spin 1 particle, but to a spin 2 particle. Okay, and again, this holds at the linearized level. Very good. So for us, it will be a very central property of amplitudes in gravity, and in fact, our constructive techniques will be geared towards constructing amplitudes which have by construction this invariance under these infinitesimal coordinate transformations. As for the spin 1 particle, asymptotic states for gravitons will be transverse, and they will be represented by a polarization tensor, which is symmetric for the graviton at least, and which is transverse. We will also take for the graviton corresponding to the fact that this is traceless. Okay, so these are the properties of the polarization tensors. It turns out that when you go to momentum space, this there is a residual gauge freedom which allows you to do a transformation in the following form. In which you have that transforming this into itself plus p mu q, let's say q nu plus p nu q mu, still doesn't change the property, provided that we are having the fact that, of course, q has a zero scalar product with momentum. Q here is, I guess I'm using the word reference vector, reference momentum too many times, but this is, you can think about this as the parametrizing the linearized diffeomorphisms that preserves these conditions. Very good. And now the next step in representing amplitudes involving gravitational fields is to use the formalism which we have developed so far, namely spinor-helicity, in a way that also can be extended to polarization tensors. And the representation for that, I mean, the extension is quite trivial, I should say. So we can represent polarization tensors, right, for a graviton with a certain polarization, say the plus polarization, which I represent now with two pluses, by using two copies of the polarization vector, which we have introduced in lecture number 1. Same thing here can be done for the negatively polarized graviton. And we are having, and here imagine that we are having the expressions in terms of spinor-helicity variables that we introduced in the first lecture. So after you have done this, in principle, you can actually try to bootstrap the amplitude. Forget about expanding the Einstein-Hilbert-Lagrangian. You can say, I think I claimed at some point, that amplitude at 3 points can be reconstructed in many cases just by using the correct helicity weights. So this will be done. So this is the amplitude, say, I mean, just for definiteness, two negatively polarized gravitons, maybe, this is an interesting question, two negatively polarized gravitons and one positively polarized graviton. Just for concreteness, we can just say that up to a constant, we can set this to be equal to the only. Remember, of course, that in 3 points kinematics, let's see, in 3 points kinematics, we are having that only the square spinors or the angle spinors are non-zero, but not the other. So in this particular case, we can have that. Let's just consider this with, hang on, instead of h, let's call this n, and 3. And let's make an ansatz about this that is constrained by imposing the fact that this has the correct helicity weight. So in this particular case, since we have legs 1 and 2 with negative helicity, this would be 1, 2 to the 6th, and then 2, 3, 3, 1. Both of them squared in terms of angle brackets. So in other words, we can use an expression for a 3-point amplitude in gravity, which can be reconstructed together with dimensional analysis by the requirement that the helicity weights are correct. This constant actually can be identified with the gravitational coupling constant. This will be proportional to kappa, but there is, if you want to relate this to the Lagrangian, you have to work out what is the correct proportionality factor. What is interesting here, however, is not just, as I mentioned before, that this is a very simple expression compared with 120, 100, more or less 100 terms you have here. It is the fact that this is also closely related to the Yang-Mills amplitude between gluons with the same polarizations. Namely, it's the square of the amplitude. So the question one can ask is whether this structure or this relation is something that can be generalized to higher points, or perhaps even higher loops or not. And this is, in a sense, the heart of the double copy constructions. Okay, questions so far about the general setup? Very good. So the first setting in which we may attempt generalizing this relation, it is, of course, at 4 points. At 4 points, one sees that some additional information is, in a sense, needed to get this to work. And at 4 points, you can see already the salient elements of the double copy construction. So this is a place where we can learn a lot. In particular, I would like to take one step backward and discuss representations of amplitudes for Yang-Mills theory before we get to squaring them. Okay, so taking one step backwards, we consider amplitudes Yang-Mills at 4 points. This is an amplitude between 4 gluons, and we write this in the following form. So, aside from coupling constant, we write this in a form in which, and let me specify, now I am discussing an amplitude which is not color ordered. So in here, color factors will be present, and we write this as the sum of terms corresponding to each exchange channel. I'll tell you in a second what these objects are. So the general organization, think I try to prepare you for this sort of organization so that some of these terms have already been used. One first thing to note is that since this is a color-dressed amplitude, we need to have color factors. So all the group theory information is in this C, S, T, and U. ST and U representing essentially the channels which we are considering. So for example, CS will have the normalization of FA1, say A2, X, FA3, A4X, which remember that at some point we introduced our F tilde, and these are the natural normalization for the structural constant, which we want to use. Okay. And then we have of course, here we see ST and U, 1 over S, 1 over T, 1 over U being coming from the propagators, and then we have everything else which is in the numerator factors. And you would say, wait a second, what happened to the contact term in here? In principle, the contact term can be absorbed by this, by having the corresponding numerator factors be multiplied, have a term proportional to the inverse propagator, so that it is, in a sense, still a contact term, but it is hidden into here. Specifically, let me just write a term here. And this is something I wrote already when, I think on the first day, when I was trying to work out the amplitude between 4 gluons. So there is a term in the numerator factor for the S channel, epsilon 1 dot into P2 epsilon 2 mu minus 1 2 exchange, and this object is multiplied by a corresponding term. This of course comes from the 3 vertex, right? So we are going to multiply this by the other 3 vertex. This is straightforwardly obtained by sending 1 to 3 and then sending 2 to 4, so relabeling on the indices. Yeah, so of course it's better not to write it explicitly, we just lower the indices in that particular case. Okay, 3, 4, 3, 4, very good. And then there is, as I just said, there is a term here which is proportional to S. So this is the new term, right? I didn't write this on the first day, partly because it was equal to 0 in that particular choice of reference momenta which we had, and partly because I consider that to be an independent graph and was not absorbed in one of the 3 graphs. 2, 4 minus epsilon 1, epsilon 4, epsilon 2, epsilon 3. Okay. Very good. Okay, so again, this is not the whole contact term. The contact term had other parts, but they have been distributed in the different numerator factors for this. How do you get the other numerator factors? Well, that's in a sense the easy part. So we're having that NT. Actually, let me just say CT is equal to CS and S acting with the following permutation. 1, 2, 3, 1. So we are cyclically permuting 1, 2, and 3 and leaving 4 as it is. And same thing with CU and U, in which we are having a different permutation, actually. CS and S, in which we have 1, this goes into 3, 3 goes into 2, and 2 goes into 1. So we have the opposite permutation of these 3 indices. Okay, very good. Okay, so one first thing to do in this language, and note that I have not used spinorilicity. Partly is to actually remark the fact that spinolanicity is independent construction with respect to double copy and color kinematics. Part of it is because I really care about gauge invariance, and I want to keep constraints by gauge invariance explicit, as in you have with a covariant notation. Okay, questions so far about what I wrote? So if I give you an amplitude in that form, the first step or operation which you can do is to check gauge invariance. This is done. I actually will not give you, it will not put all the algebra on the blackboard. This is the result of a short calculation. And it turns out, of course, gauge invariance would be straightforwardly implemented by having this epsilon replaced by the corresponding momentum, but you're not expecting gauge invariance to be to leave individual numerators invariant, right? Instead, if you do this calculation explicitly, you'll find the following relation. We're going to have a constant here, S, so it's a contact term, the gauge variation of this, and then there's going to be an expression. I give you the expression, but I do not care so much what it is. I care about the fact that this is cyclic symmetric. So namely, this is the product of polarization 1 and 2, polarization 3, say scalar product with P2 minus P1. We can write it in this way, plus cyclic. This is the result of a straightforward calculation, which I would encourage you to perform. And what is important here is that, of course, this is like a cyclic permutation of 1, 2, and 3. What does it mean? It means that this thing, which I can actually relabel as altogether, I can say this is S alpha. This alpha of epsilon and P is going to be the same for all channels, right? Because it's cyclic symmetric, whereas the other numerator factors are obtained by acting with a cyclic symmetry, one way or the other, by a cyclic permutation on the S1. So the result of this short calculation is the following, that the full gauge invariance of all the amplitude, I mean, the amplitude is gauge invariant, of course, but the question is, how does the zero arise? This is a question that interests us greatly. And the result of this is that, sorry, the minus sign here is kept out. This is alpha epsilon P, and then CS plus Cu plus Ct plus Cu. So in other words, this is equal to 0 because of Jacobi relations. So all I needed to get a 0, and keep in mind here that I have sort of specialized on the case in which you have an explicit expression for the color factors, but all that needed to be used for getting a 0 is this particular algebraic relation between the color factors, which for us is very fundamental, comes from, well, it's Jacobi relation, so it's one fundamental property of the structure constant, of a pair of structure constants, but this is all I needed to use. Okay, very good. Questions about this? So another property which you can verify very quickly, but takes you a little bit more algebra to do that. That the numerator factors I've wrote over there are equal, obey the same algebraic property. They have the same algebraic property as the color factors. Let me just mention it. Take some algebra. This is, takes a bit to verify this. So this property is a first manifestation of what we call color kinematics duality. Namely, the fact that we can find sets of color factors and sets of numerator factors which obey the same algebraic property. And in this particular case, it's singular, like there's just one of such relations which needs to be obeyed, but as we go to higher multiplicity and perhaps to loops, we'll find more relations stemming, all of them stemming from, in simplest case at least, from Jacobi relations, and also in more complicated cases from other properties of the color factors, such as if you have matter commutation relations of the representation matrices. Okay, so the next step I would like to suggest is the fact that having identified a set of objects that have the same algebraic properties as the color factors suggests that perhaps we can take a look at the following object. Take a look or inspect at, let's call this, so we have A4, this is a 3 level. Let me just be uniform about notations there. And we replace the color factors with a second set of numerator factors. In the simplest incarnation, just take the same numerators. And then, well, if you like, you can also map, specify a map for the Yamin's coupling constant. So what is this realistically? This is going to be equal to, well, there's coupling constants here squared, and then we're having ns tilde plus nt tilde plus nu tilde divided by the corresponding propagators. So the question becomes, what is this? And I would like to suggest this, in a sense, as a natural operation you can do by having objects with which, by introducing objects which have the same properties, have the color factors, thereby suggesting that they may be interchangeable. We will call this the double copy for reasons which are obvious, right? Unless, I mean, if you really want to have a double copy, then you don't have, you have a second copy of the ns and t and u, as opposed to one denoted with tilde. This is slightly more general situation. But the question I would like to ask still is, what are the properties of this object, and what is, for example, the corresponding gauge invariance? So questions so far about the question? Hopefully I have 15 minutes and I can partly answer this question, which is kind of very good. Okay. Okay. So the simplest thing I would like to do is to keep the polarizations labeled in different ways. So it can be the same amplitude, or they can be coming from the same amplitude, but I won't allow myself the possibility of having left and right polarization which are not the same. But also I could do this by pairing the polarization in the same way. There will be a very elementary difference between these two options, which I think it's already quite instructive. So the first property, I mean, of this object will be that external states and let me just say that, I mean, something which is implied there, but it doesn't. This formula does not make sense unless I have same momenta on both sides. So what I mean here is that S, T, and U are the same, and the dependence on the momenta. Here we still have the expressions, right? So again, you can put a tilde here for this, but P1 is the same on both cases. Otherwise, I don't really know how to make sense of that thing. I would have to tell you something more, right? I would have to tell you which of the S's or which of the T's you pick up, since they will be different. So having established this, we still have a notion of 4 asymptotic states, and we still have a notion of 4 asymptotic states coming with those definite momenta, which are the same on the two sides. And each, the external states, or the asymptotic states, will be characterized by, I can attach a polarization tensor to that, which is, if I want to keep a tilde, does not have definite properties under symmetry. And I think this is something which was done also in the other course, that, well, okay, sure. So we can decompose this into a symmetric part. Let's make it traceless. We can decompose this to an antisymmetric part and then a trace part, if you like. Okay. Very good. So if we identify in this particular case, really, we take away the tilde, what we would end up having is a symmetric tensor, which is also, by construction, traceless for a particular set of polarizations I picked up. So I picked up no polarizations. If you flip back in the notes, you'll find that they have that properties, and so that would make them, it would make them also traceless. With a different choice of polarization, that would not be the case. Okay, so more importantly here is gauge invariance, or what principle of gauge invariance can we assert? So in this particular case, gauge invariance is still intact. Namely, I can replace epsilon, one of the epsilons, shall we say, with the corresponding momentum. So it doesn't necessarily need to be number 4 in this particular case. And then I can do the following operation. In the tilde polarization corresponding to the same one, I just, well, I just keep it, but I change the name, and this becomes Q, a reference. Momentum, which we know that has the property that its scalar product with momentum is equal to 0, which now gets slightly reinterpreted. It was transversality of the other polarization, but here we just reinterpret it. So why do I say it is still gauge invariance? The heart to this is the fact that, well, I have not just used any set of numerators, but I've used the same set of numerators which obey this color kinematics condition. Okay, so if you go through the same steps of the argument for gauge invariance, that still goes through. And in fact, it is perhaps worth doing this explicitly. So namely, yeah. Mm-hmm. Yeah. Yeah, I mean, I could. So sorry, other core. What do you mean for other coordinates? I mean, what do you mean for it is part of other core? Yes. Mm-hmm. I mean, they are still part of the same space-time, right? But yeah, they can be different. Yes. Yeah. But we are still. I mean, we're not saying that the polarization live on different spaces. They are still part of the same four-dimensional flat space-time. Yeah. Okay, and which is part. I mean, I think this is an important thing to remark. Yes. Very good. Anything else over there? Okay. So if I want to consider now the gauge transformation of this, I will focus in particular on a particular kind of gauge transformation. So we just look at up to a constant, our double copy organization of numerators. And we have, say, epsilon. Well, let's do this for leg number 4 for concreteness, since we are having some formulas which specifically apply to that, and we are considering the following. So this is Q4 Q nu plus P4 nu Q mu. Okay. So what is the result of this operation? This is going to be equal to, well, there will be two terms. Should have enough space to put them orderly linear. So we do the same argument, and this is going to be equal to ns plus nt plus nu, in which all I have done is really for this will be the second term in here, sending epsilon 4 to q, and this is going to be equal to alpha of epsilon tilde at this point would be of the tilde polarization, and the p's are the same as we said, right? This would be for the second term. The first term would be the same with flipping the tilde or untilded object. This is, yeah, we have epsilon 4 tilde becoming q, same q between the two, and then there's this multiplies alpha of epsilon p. This is the same result up to a sign for obvious, for reasons that I'm, yeah, maybe a suboptimal choice of notation on my end, but that's the same result up to a sign. And the highly non-trivial statement, which is quick to verify at 4 points, but this is what is difficult to construct at higher points, is the fact that we can find numerators for which this is true. For now, on both sides of the double copy. So this is the consequence of the CK duality. Okay, very good. And here we have assumed that, I mean, a technical part here is that when I specify I want to attempt these gauge transformations, we have assumed that Q is as a zero scalar product with P4. And when I have to show that color kinematics duality, I mean that you can find numerators which have these properties, they need to hold, that property needs to hold for all transverse polarizations, not just for one or the other polarization. So that is what has been used. So in particular, this property needs to hold as long as I replace the polarization for any transverse Q. Okay, very good. But then you already know what this gauge transformation is, right? This is the one corresponding to linearized diffeomorphisms, as I explained or stated before. So this suggests that whatever this mystery object is to be interpreted as a theory which is a theory of gravity, because it has the gauge, the gauge symmetry associated with spin 2 particles. So this is, I want to say, the heart of the double copy construction is the fact that you are manufacturing a set of amplitudes which have this invariance under, which is expected of gravitons, but also comes with, I want to say, a potential subtlety in that you know that this is a theory of gravity, but you do not know which theory of gravity it is. And in particular, if you don't consider supersymmetric cases, you're going to have extra stuff. It's not just going to be Einstein gravity, it's going to have extra states. And you can see right away, just by looking at what I put in the blackboard, that this is the case. Because we have those states in which the indices mu and nu are not necessarily symmetric in the polarization. So there's extra stuff corresponding to an anti-symmetric object and also to the trace that is to a scalar. And in fact, if you run through the very same argument, but you say, take the anti-symmetric part over there, you would end up having the gauge invariance property corresponding to the tensor field. Okay, very good. So this is a very good moment to stop and, of course, open up to questions. What comes tomorrow is us getting a little bit deeper into the properties of this object here. For example, I would like to relate this to relations involving partial amplitudes, color-ordered amplitudes, right? I've kind of spent all this time into introducing partial amplitudes, so why don't we use them? Why don't we phrase our double copy in terms of those objects? Actually, we'll do that and recover the KLT formulation, which is where this structure was first observed in string theory. I would also like to ask the question of what can this construction teach us about color-ordered amplitudes, and we will see that there's a very important set of relations. At some point when we were discussing Kleist-Coif relations, I said, well, so now we have n minus 2 factorial partial amplitudes which are independent, right? Not really, there's extra relations, so we will discuss those extra relations. And also I would like to say a little bit about generalizations at higher points and generalization at loop level. Okay. But for now, it's over, except let me ask you, do you have questions about anything you see on the blackboard right now? Yes? Yes. Yes. That's very good. So this is not, I mean, this is an operation which destroys information in a sense. But yes. Yeah, very true. Anything else? Mm-hmm. Mhm. Yes, yes, yes. So the key, this is a very good observation. So the key thing here is at 4 points, everything is under control here, right? But are we sure that the only algebraic relations that the color factors will satisfy for, say, a theory of write down are going to be the Jacobi relations or stemming from the Jacobi relation, or do you have extra ones? In some cases, of course, you're going to have extra ones. Now, a question which becomes imperative is, at a certain multiplicity, do you need those extra relations to prove gauge invariance, or is it just the Jacobis? Okay. So a lot of people like to phrase the double copy just by using a generic gauge group. So not committing on the color factor and saying, well, if it's a generic gauge group, although there's not such a thing like a generic Lie group, right? I mean, they're all classified, they're all special cases in a sense. But what people really mean is, I am assuming Jacobis, say, commutation relation of representation matrices and nothing else. And then this is, of course, easier in this particular case to impose those corresponding relations on the numerator factors. Or you could use your favorite gauge group, but you need to be very careful, because whenever you're using, even implicitly, one extra relation for your color factors, and that is necessary for gauge invariance, then you need to impose the same thing on the numerator factors, and imposing relations on the numerator factors can be hard. Okay, but we will see more about this tomorrow. So please let me know if there's any additional question. Otherwise, we'll get ready for the next lecture, I guess. Yes, so 10 minutes maybe, shall we say? Okay, so please be back in 10 minutes, because otherwise we are having problems. Yes, thank you.